Good afternoon, everyone. It's been a big 3 days. I hope you've all learned something. I hope you've got a little bit of energy still for me to get through this last session. And yeah, I'm just trying to explain and hopefully shed a little light on how you can use the internet as your load balancer. So, as Jamie said, I'm Martin. I am an Australian who moved to Germany 13 years ago. I've worked in network and system administration for over 2 decades now, so seen some things. When
you can't say something like that and just leave it hanging.
You can ask me anything you like over beers later. So when someone talks about load balancing, like the thing that most people come to mind is a very self-contained system. You have your workload arrives on your system. There's some kind of single point of concentration, and it load balances your work onto the targets that are all, contained within that system. That load balancer might be an appliance, or something built into your networking equipment. Back when I started in the industry, those targets were almost certainly physical machines. These days, they're probably VMs, containers, queue ingestion, whatever. But what if your targets are not all in one place? What if your targets are spread around the world, across continents, across countries? How do you control the work arriving on these systems? For big companies, this is the kind of work that your edge team will work on. For everyone else, this is the kind of thing you outsource to a CDN. So how do we load balance at internet scale? Your two main options are DNS or routing. If you have full control over the client side, maybe it's a mobile application or a single page website, then there may be other options available to you. But if you don't control the client in that way, then these are the two sort of main areas that you can use to control how that work is arriving on your systems. So let's start with DNS. The concept of having a domain name that resolves to different IPs when it's looked up is a fairly straightforward concept. Whatever service is acting as your authoritative DNS responds with a different IP depending on who is asking. The complexity is in how you figure out which IP you're going to reply to every request. One input that we can use into that decision-making process is IP geolocation. So there are databases that people will sell you, and they'll update them on a regular basis. And they supposedly will map an IP to a location down to the country, state, city, or even a postcode. They'll also include some other metadata, so the network that IP tends to be hosted inside of and things like that. So this kind of data can allow you to make incredibly nuanced decisions. You can choose an edge location based on the physical or topological information that data is telling you. However, those decisions are only as good as the accuracy of that data. So IPs, they can be reallocated to different networks. They can be repurposed by the current network that has them. They can be dynamically assigned and move around. Or the location just starts off inaccurate in the first place. There's some false assumptions or conclusions that the data provider has taken. A very common error is a large IP range that is geolocated to the headquarters of that network instead of being distributed where they're actually using those IPs throughout their national network, say. So another problem that you have is you only really have the IP of the DNS resolver. Okay, the request is coming from a resolver of some kind, and that's not usually the client itself. This is a problem if the resolver location is not representative of the clients. So this might be because the ISP has a very concentrated resolver cluster. Maybe they're a national ISP here in Australia, but they only run a DNS resolver cluster here in Sydney. So your client's in Perth, DNS resolver in Sydney. Brisbane, DNS resolver in Sydney. The other situation that's common is when the client has configured a third-party resolver. So if they're using Open DNS or Google's public DNS, then there's no relationship between where the client sits in the network and where the resolver sits in the network. Maybe they're close together, maybe they're not. Some resolvers support EDNS client subnet or ECS. So this is where inside the request, they'll actually give you a hint at the client IP. They don't usually give the exact IP because that's not great for caching and that's not great for privacy, but they usually give you a hint at what the client IP is, and so then you can actually use that in your decision-making process rather than the resolver's IP. Unfortunately, not all resolvers support ECS, and not every client wants them for those privacy reasons. There's some people that, even some of these third-party resolvers support ECS. They offer a service where you can configure them so that you don't have ECS and you're not forwarding that hint to the authoritative servers. So an alternative input to the decision is where the DNS request is processed. So presuming that the subsequent connection will come over a similar path to the DNS request, the IP you reply with can be based on the location of that authoritative DNS server. However, that requires that your authoritative server locations are aligned with your edge locations. That's not so hard if you're running both of them, but if you've outsourced one or both of those, then it's perhaps not easy to make sure that, for every DNS location there's a matching edge location and you have a good, mapping between the two. Again, this usually only tells you something about the location of the DNS resolver. And as we talked about previously, the resolver is not always representative of where the client is. There are also some concerns in the basic idea of a DNS solution. Okay, so DNS responses are generally cached at the client and resolver level to reduce query load. Even though you can suggest how long they should cache that request, that response with for, they don't have to, honor that. They can enforce a minimum time. So say you put in 60 seconds and they enforce 5 minutes as a minimum time. They can ignore your suggestion completely and just hard code everything to half an hour. If you want to change the IP you're responding with, perhaps due to something failing or a desire to turn on a new POP or whatever like that, the caching can delay the propagation of that IP through down to clients. So it's not all bad news for DNS though. This kind of solution is very stable. So after that client has resolved that DNS name, they've got an IP and they'll just keep connecting to it. If the TCP session dies, they'll just reconnect to that same IP, and so they'll continually hit that same edge location over and over again. It has the potential to give you good control. We talked about how you can be very nuanced with that IP you're returning. So selecting it based on all those parameters, and you can vary about that resolver gets that IP, that resolver gets that IP, and go from there. So a quick recap. Varying DNS responses is one method to direct requests, but the concept is simple. The implementation details and the operational complexities can make things difficult. The alternative load balancing solution is using the internet routing system to guide requests onto a specific edge location. So one of the important concepts I'm going to talk about today is Anycast. But in order to understand Anycast, it's probably easier to start with Unicast. Unicast is how most routing works. A single location in the internet, announces the route, and all traffic flows to that one location. It's deterministic and it's reliable. Anycast is when the IP is advertised from multiple places within the network, and it's the routing system that figures out where those packets are going to flow to. Anycast is used by many UDP-based protocols. DNS is the obvious example. ISPs will use Anycast inside their network, so that that configured resolver IP that they tell everyone on their support page routes to a nearby cluster or server. The DNS root servers use Anycast. So even though there's only 13 configured IPs, The root servers are actually hundreds of servers spread around the world. But a connectionless protocol like UDP works just fine with Anycast. A connection-oriented protocol like TCP, it needs a stable path. It needs the packets for a single session to follow the same path so that we're always going to go to the same location. To illustrate the pathological case, an unstable path between the client and potential servers, let's walk through a TCP handshake. A connection is coming from the client on the bottom left there. The SYN packet is routed to the edge location at the top right. The server returns a SYN ACK packet back to the client. The client sends an ACK packet, but instead of being routed to the same edge location, it's routed to a different one. That server that receives the ACK packet has no connection state for this client and sends a reset packet. We have one very confused client who may or may not retry the connection in a timely manner. So let us talk about how to get stable paths between clients and edge locations. It's possible for internet routers and firewalls to utilize multiple upstream links, each with just a simple default route. The internet connections can operate in a sort of load sharing or active backup mode. And this equipment should operate with session affinity. So this is when they persistently use the same upstream link for the life of a single TCP session. Alternatives like per packet load balancing can lead to that unstable paths and connection resets like we talked about. The next case we need to consider is routers participating in internal or external routing systems. ECMP is equal cost multipathing. This is the routing algorithm installing multiple paths to an IP range because it calculated them as equal. One of the paths is selected by a hashing algorithm. Persistently routing the packets of the same TCP session over the same path requires consistent hashing. This means that the inputs to the hash need to be stable for the life of the TCP session. Typically, this means you can only use the source and destination IPs as inputs to the hashing algorithm. Any other inputs to the hash are likely to make it inconsistent and hence unable to ensure stable path selection. As we spoke about ECMP, there was mention of routing algorithms, and it's important that we dig into that aspect a little deeper. When networks exchange routing information with other networks, they require an external gateway protocol, and the de facto one in use on the internet is BGP, or Border Gateway Protocol version 4. In order to maximize the potential for stable paths, we need the BGP algorithm to be deterministic to minimize or eliminate churn between alternative paths. So the BGP route selection algorithm has up to a dozen decision factors, but I'll just focus on the most important ones. So local preference is an extremely large hammer that can be used to override all other tiebreakers. It's usually statically configured, and it's essentially an expression of a network's routing policy. A typical configuration would prefer downstream routes over upstream ones, but it can also be an expression of other policies like preferring cheaper paths over more expensive ones, or preferring higher capacity paths over smaller ones. Because the configuration is typically static, it is also deterministic. BGP is a path vector protocol, and that surfaces in the AS path attribute. AS stands for autonomous system, so essentially a network under the control of one organization. Each AS has a designated number referred to as the ASN. The network that announces the IP range puts its ASN in the attribute, and each AS that the route is passed to adds its own ASN to the front of the list. The attribute is also used for loop detection, but for our purposes today, it's just important to know that BGP prefers a shorter AS path. As long as our source of the route is stable, this tiebreaker is also deterministic. MED is multi-exit discriminator. If the design of this was for two networks that interconnect in multiple places, they can apply MED as they export routes to signal their preferred location for receiving traffic for that IP range. However, the network receiving those announcements can choose to honor that expressed preference or not. If they want something different to happen, they can override the MED attribute itself, or they can manipulate earlier attributes, so MED is never considered. We have been discussing BGP used externally, so eBGP, but it can also be used internally, iBGP. The next tiebreaker is preferring routes received via external BGP over routes received via internal BGP. This means that BGP prefers to send packets out of the network as soon as possible. This is our last deterministic tiebreaker, and so a router configured to do ECMP will have stopped at this point and would install the remaining equal paths. BGP will prefer a route it received earlier over newer ones. This is designed to prefer more stable paths that have not changed recently. However, it's not deterministic and causes route churn when the oldest path is interrupted. If BGP is still trying to tiebreak at this point, it's getting desperate and uses attributes that have little to do with the quality of the path. Router ID is usually the primary IP address of the neighboring router, and BGP prefers the lower router ID. If two BGP sessions go to the same neighbor router over different circuits, then the algorithm will prefer the routes received over the circuit with a lower IP address. Both of these tiebreakers are deterministic, but they are also completely arbitrary, and it's the computing equivalent of deciding something with a coin flip. So in summary, BGP can choose multiple stable paths as long as you stop tiebreaking early enough. But we're not quite done talking about BGP just yet. Anycast has a goal of packets being routed to the nearest edge location. But if you think back to the tiebreakers, there wasn't actually that much that was optimizing for nearest. The closest is AS path, but it's explicitly a path vector and not a distance vector. An ASN is one AS, no matter how big or small that network is in reality. A tiny local network is counted the same as a global one. If you imagine each of these ovals is a single ASN, then BGP will treat the path from A to B as equal to the path A to C, despite B being topologically much closer than C. But AS path was overridden by local preference. That means a network's decisions about how they want to run their network take precedence. If they decide that latency and performance are not important, they can configure a policy that optimizes for other things like cost. To achieve performant Anycast, you need to understand which networks will do things like that and come up with an interconnection strategy that plays into how they want to run their networks. A good example to illustrate this problem is the United Arab Emirates, a location with very expensive connectivity. Unless you find a way to connect directly with local ISPs, either with a direct circuit or via an internet exchange, they will prefer to exchange traffic with you in Europe. They can get submarine capacity back to Europe cheaper than buying local transit capacity in the United Arab Emirates. So ISPs would prefer to exchange traffic in Marseille, adding an extra 80+ millisecond round trip because it will save them money. You need to find a solution that ensures the traffic stays local if you want your Anycast to remain performant. But there will always be a subset of networks you can't reach directly. You will exchange traffic with them via your transit providers, and shaping how they route towards your systems can be done using BGP communities. Communities are labels that you can tag your routes with as you export them to your transit providers. Each of them has a different meaning, indicating to the provider that they should handle that route in a non-default way. One possibility is asking them not to export that route to a particular ASN. Another one is to not export that route outside a particular country or region. Another alternative is that you want them to handle it with a different local preference inside their own network, so that as that route propagates through their network, it behaves differently. So in summary, you can turn the internet into your load balancer in using Anycast and focusing on these two areas. You pay attention to which networks you connect to and where. You select which routes to announce in which locations to which networks. And you use communities to tweak how those routes reach the far corners of the internet. This is SREcon, so of course we have to talk about SLOS. Based on historical trends and analysis of the current situation, we should be able to determine a number of goals. Round-trip latency, throughput, retransmissions due to packet loss are all relevant measurements which we can evaluate our performance with. What our goals are for each measure will vary by location and network. Some regions have higher quality infrastructure than others. Some networks invest more in capacity and maintenance than others. And sometimes you can't tell if there's a problem you should be troubleshooting, or if that packet loss is just someone browsing social media while on the toilet where their Wi-Fi signal is terrible. So let us discuss a little how to collect measurements at internet scale. One of our vantage points for measurements is the routing equipment in each of our edge locations. Most modern network equipment can sample the traffic flowing through it and emit details that can be collected and aggregated. Typically, you learn the duration of the flow, the IPs and ports, the packet counts, total bytes transferred. Given sufficiently large traffic volumes, you have to reduce your sampling rate and aggressively aggregate the data ingested at your collector infrastructure, but you still have a usable picture of how much traffic is exchanged with particular IP ranges and networks. Although flow analysis can be helpful, you are limited by the equipment vendor's implementation and how configurable they've made it. You can collect more detailed and customized network metrics at the server operating system level, but that is perhaps not the best vantage point available to us today. As you might have, if you were in the talk here previously, recent advances in BPF mean it's now possible to collect detailed custom network metrics at the driver or even hardware level. This is particularly useful if you're also handling packets with BPF to process them in a non-standard way, say to protect the operating system from denial of service attacks. That packet is never going to get up to the operating system level, so if you're doing your observability at the operating system level, you're not going to count that and you'll never see it. To help analyze TCP performance, we can measure many things on a per session basis: round-trip latency, jitter, retransmissions, maximum segment size, window size, effective throughput, socket reuse. We can also use weighted sampling to aggregate away uninteresting details and retain more data that helps us with troubleshooting anomalies. But so far, we're only measuring inside our network. We're operating at internet scale, and we also need to measure at that same scale. We need to understand the reachability and performance of our system from outside our network. One way of collecting these measurements is from probes in other networks. We could run these probes ourselves. We could purchase access to a vendor's probes, or we can utilize community projects like RIPE Atlas. So RIPE is the Internet Resources Organization for Europe, the Middle East, and parts of Central Asia. Their Atlas project has been distributing hardware probes for free to a wide variety of internet industry people, and they tend to be collected to home networks and provide measurement vantage points inside a large majority of ISPs. You can create ad hoc measurements or schedule regular ones. There is a variety of measurement types, including trace routes, DNS lookups, and HTTP tests. I think this one was some trace routes from an American ISP to our infrastructure. Although the external probes mentioned so far can be very helpful, they still sometimes fail to capture the actual client experience as broadly as we would like. This is where real user monitoring, or RUM, can come into play. By instrumenting the client, we can report on their side of the TCP session, capturing information we don't have on the server side. We can also incorporate experiments, like testing a TCP session to an alternative edge location, which we can then compare to the primary TCP session. Although the measurements we collect during production operations can help us analyze the system and troubleshoot problems, sometimes we need data specific to a particular client who is reporting a problem. We could walk them through using the operating system or third-party tools to do that troubleshooting, but that can be hard for non-technical users. Debug websites can do this for us. The client just needs to visit the URL, and then RUM-like tests are run on their behalf and get them the measurements we need. Here is some sample debug output I took while tethered to my phone. It nicely highlights the 4G networks have decent bandwidth, but relatively poor latency. So we did it. All that hard work defining, implementing, and monitoring an internet scale load balancer. And in a steady state, everything is fine. But now something has happened, and we are seeing too much load arriving in one or more locations. It's not organic traffic growth, so it doesn't need a permanent solution, but for the next hour or 3, we need to move traffic elsewhere. If we went with the DNS solution, we can adjust some of the IPs we were returning to relevant resolvers. Calculating how many responses we need to change can be tricky, as the ratio of traffic per DNS request varies greatly, from resolvers used by a single person at home through to ISP resolvers used by thousands or millions of people. Done early enough, any change will propagate through the DNS caching before the traffic levels become problematic. But what if we don't have that much time? What if traffic increases too quickly and we need to respond faster? This is where we can use Anycast to backstop our Unicast DNS solution. By switching from Unicast to Anycast during incidents, we can stabilize the system quicker. Presume that one Unicast IP range assigned to a particular edge location was a /24. From larger edge locations with excess capacity, we can announce the supernet, say a /20, that contains that /24. Because BGP prefers more specific routes, it'll go to the /24 for now. If the original edge location becomes overwhelmed with traffic, we can stop announcing that Unicast /24, and traffic will start routing via Anycast to the larger locations that are announcing the /20. Some TCP sessions will be interrupted, but not as many as would be affected if we allowed the traffic to continue to overwhelm the original edge location. If our original solution was Anycast only, we can shed load by withdrawing some or all route announcements from the affected edge location. Traffic would ideally be rerouted to higher capacity edge locations or diffuse across enough other edge locations to not cause cascading load issues. However, rerouting traffic in a nuanced fashion can be tricky. On the internet, a /24 route is the smallest IP range that is generally accepted by other networks. This means that you can generally only announce or withdraw routes in a minimum of /24 increments. You have to make a trade-off between a /24 being a proportionally large amount of your traffic in a location, or you need a lot of /24s to shard your traffic over, wasting precious IPs and polluting the global routing table with more routes. The load shedding techniques we just discussed relied on adjusting the ways that we guide traffic into our edge locations. But another alternative is we can redirect some TCP sessions to a different edge location, which then replies directly to the client. When the SYN packet arrives in the first edge location, a BPF program can decide to shed this session. It then forwards the SYN packet to another edge location with spare capacity. A server in the second edge location accepts the connection and sends a SYN ACK packet directly back to the client. The client responds with an ACK packet which the original location forwards as well, completing the handshake. The TCP session then proceeds with this triangulation ongoing throughout the life of the connection. Load shedding via direct server return allows us to be extremely nuanced with how much traffic we shed. Because we can differentiate down to the individual TCP session, what we shed can be based on anything we know about that connection. Client IP or range, client RPS, a traffic type, anticipated traffic volume, anticipated session duration, and many more. Direct server return has very few downsides, but it does require we spend some precious resources at that overloaded edge location, forwarding packets to the second location for the life of the session. It also means that both locations are points of failure for this redirection sessions, and both need to remain healthy for the duration of the TCP session. And we've likely added some latency, sometimes a little just due to that triangulation, but sometimes significant amounts if that second location is much further away topologically. The other edge location might not also have the best paths back to the client due to being in a completely different topological location. So those are the ways we can shed load, either changing how requests arrive at our edge locations or forwarding some requests to a different edge location. To wrap up, I'd like to revisit the subtitle of my talk that was poking a little fun at ECMP. ECMP is everywhere in the networks of today. There is ECMP in ISP networks. There is ECMP in global backbone networks. There is ECMP even inside edge locations. It's ECMP all the way down. And that's all I have time for today.